This lesson is on solving problems involving the determination of the pH of acidic and basic solutions. This is part 3a on diprotic and triprotic acids. Solving for the final pH of an acidic or base solution will depend on the relative strength of the acid or base solution respectively. Let's do a brief view of polyprotic acid ionization process, all at equilibrium. Polyprotic acids undergo two or more ionizations in consecutive manner. Example 1 is H2C2O4 or oxalic acid. In the first ionization process, aqueous H2C2O4 in liquid water ionizes partially to produce hydronium and HC2O4 minus or hydrogen oxide ion. Ka1, or the first acid dissociating constant, is 5.4 times 10 to the minus 2. The second ionization process is aqueous hydrogen oxide ion in liquid water ionizes partially to produce hydronium and oxide ions. Ka2, or the second acid dissociating constant, is 5.3 times 10 to the minus 5. Example 2 is H3PO4 or phosphoric acid. In the first ionization process, aqueous H3PO4 in liquid water ionizes partially to produce hydronium and dihydrogen phosphate ions. K1, or the first acid dissociating constant, is 7.5 times 10 to the minus 3. In the second ionization process, aqueous dihydrogen phosphate ion in liquid water ionizes partially to produce hydronium and hydrogen phosphate ions. Ka2, or the second acid dissociation constant, is 6.3 times 10 to the minus 8. In the third ionization process, aqueous hydrogen phosphate ions and in liquid water ionizes partially to produce hydronium and phosphate ions. K3, or the third acid dissociating constant, is 4.2 times 10 to the minus 13. Practice problem 1 is to determine the equilibrium concentration for all species in a 0.25 molar H2SO3 solution. Determine the pH of this solution. First, we write the two ionization systems H2SO3 undergoes, but we will look at the first ionization system involving aqueous H2SO3 in water ionizes partially to form hydronium and bisulfite ions. K1's value is 1.3 times 10 to the minus 2. One then constructs a Rice table. The initial concentration of H2SO3 is 0.25 molar and 0 molar for both hydronium and bisulfite ions. The change is minus X for H2SO3 and plus X for both hydronium and bisulfite ions. The equilibrium concentration for H2SO3 is 0.25 minus X and plus X for both hydronium and bisulfite ions. Now, one writes out the equilibrium expression for K1, which equals the concentration of bisulfite ion times hydronium ion divided by the concentration of sulfurous acid. If one plugs in the numbers, 1.3 times 10 to the minus 2 equals X squared divided by 0.25 minus X in parentheses. To see if X is small enough to ignore, one takes the concentration of the diprotic acid, sulfurous acid, and divide by K1's value to see if its ratio is greater than or equal to 400. In the end, the ratio equals 19, which is less than 400. In this case, the assumption fails, and one either has to use successive approximation or the quadratic equation to solve for X. For this problem, we will use the successive approximation method. In the first assumption, X0 equals 0, and after solving for x1, it equals plus or minus 5.7 times 10 minus 2. For this and the rest of these calculations, the positive root will be used. This process will continue until two consecutive values are equal to each other. In the second assumption, with x1 equaling 5.7 times 10 minus 2, it equals, after plugging in x1's value, plus or minus 5.0 times 10 to the minus 2. In the third assumption, with x2 equaling 5.0 times 10 to the minus 2, it equals, after plugging in x2's value, plus or minus 5.1 times 10 to the minus 2. In the fourth assumption, with x3 equaling 5.1 times 10 to the minus 2, it equals, after plugging in x3's value, plus or minus 5.1 times 10 to the minus 2. As you can see, x3 and x4's values are identical, so the final x value is 5.1 times 10 to the minus 2. Now our focus is on the second ionization process, where bisulfite ion in liquid water ionizes partially to form hydronium and sulfite ion with a Ka2 value equaling 6.2 times 10 to the minus 8. Like before, a construction of a rice table is made where the initial concentration of bisulfite and hydronium ions are both 5.1 times 10 to the minus 2 molar and 0 molar for sulfite ion. The change is minus Y for bisulfite ion and plus Y for both hydronium and sulfite ion. The equilibrium concentrations are as follows: bisulfite ion with 5.1 times 10 minus 2 minus Y, hydronium ion with 5.1 times 10 minus 2 plus Y, and sulfite ion with plus Y. Now, like before, one writes the K equilibrium expression, but now for the second ionization process, where Ka2 equals the concentration of sulfite ion times hydronium ion divided by the concentration of bisulfite ion. After plugging in the numbers, 6.2 times 10 minus 8 equals Y times 5.1 times 10 to the minus 2 plus Y in parentheses, divided by 5.1 times 10 minus 2 minus Y in parentheses. To determine if Y is small enough to ignore, one takes the concentration of bisulfite ion and divide by its Ka2 value to see if its ratio is greater than or equal to 400. It turns out that the ratio equals 8.2 times 10 to the 5, and since the ratio is greater than or equal to 400, the assumption Y is small to ignore is valid. After revising the equation, Y equals Ka2's value, or 6.2 times 10 to the minus 8. The final answers are as follows. Hydronium and hydrogen sulfide ions concentration equals 5.1 times 10 to the minus 2 molar. Sulfurous acid has a final molarity of 0.20 molar. The final molarity of sulfite ion is 6.2 times 10 to the minus 8 molar. The pH of this solution equals the negative log of hydronium ions concentration, or the negative log of 5.1 times 10 minus 2 equals 1.29. The percentization is calculated by taking the part of sulfurous acid and bisulfite ion ionize and divide by its original concentration of the sulfurous acid, which is, after plugging the numbers, 20.4%. Practice problem 2 is to determine the equilibrium concentration for all species in a 0.50 molar H3ASO4 solution or arsenic acid. Determine the pH of this solution. The three equilibrium equations for this acid are shown below. The first ionization process is when aqueous H3ASO4 in liquid water ionizes partially to produce hydronium and dihydrogen arsenic ions. K1, or the first acid dissociation constant, is 6.0 times 10 to the minus 3. One constructs a Rice table. The initial concentration of H3ASO4 is 0.50 molar and 0 molar for both H2ASO4 minus or dihydrogen arsenate and hydronium ions. The change is minus X for H3ASO4 and plus X for dihydrogen arsenate and hydronium ions. The equilibrium concentrations are 0.50 minus X for arsenic acid and plus X for dihydrogen arsenate and hydronium ions. The equilibrium expression for H3ASO4 is K1 equals the concentration of dihydrogen arsenate times hydronium ion divided by the concentration of arsenic acid. In plugging in the numbers, 6.0 times 10 to the minus 3 equals X squared divided by 0.50 minus X in parentheses. To determine if X is small enough to ignore, one needs to take the concentration of arsenic acid divided by the K1's value to see if its ratio is greater than or equal to 400. It turns out that the ratio equals 83, which is less than 400. So one needs to use either the quadratic equation or successive approximation to solve for X. Like before, we will use successive approximation. Using the successive approximation method, where in the first assumption, x0 equals 0, x1 equals plus or minus 5.5 times 10 to the minus 2. For each answer, one will use only the positive root, and this process will continue until two consecutive answers are identical. In the second assumption, using x1's value equaling 5.5 times 10 to the minus 2, x2 equals plus or minus 5.2 times 10 minus 2. In the third assumption, using x2's value equaling 5.2 times 10 minus 2, x3 equals plus or minus 5.2 times 10 minus 2. This process is over since x2 and x3's values are the same. Next, we will be studying the second ionization process, where a dihydrogen arsenate ion in liquid water ionizes partially to produce hydronium and hydrogen arsenate ions. K2, or the second acid dissociation constant, is 1.0 times 10 to the minus 7. One constructs a Rice table where the initial concentration for dihydrogen arsenate and hydronium ions are 5.2 times 10 minus 2 molar and 0 molar for hydrogen arsenate ion. The change is minus Y for dihydrogen arsenate ion and plus Y for both hydronium and hydrogen arsenate ions. The equilibrium concentration is 5.2 times 10 minus 2 minus Y for dihydrogen arsenate ion, 5.2 times 10 to the minus 2 plus Y for hydronium ion, and Y for hydrogen arsenate ion. The equilibrium expression for K2 equals the concentration of hydrogen arsenate ion times hydronium ion divided by the concentration of dihydrogen arsenate ion, and plugging in the numbers, 1.0 times 10 to the minus 7 equals y times 5.2 times 10 to the minus 2 plus y in parentheses, divided by 5.2 times 10 to the minus 2 minus y in parentheses. To determine if y is small enough to ignore, we take the initial concentration of dihydrogen arsenate and divide by K2's value to see if it's greater than or equal to 400. In the end, the ratio equals 5.2 times 10 to the 5. And since it is greater than 400, the assumption that y is small is valid. In the end, after rearranging the equation, y equals K2, or 1.0 times 10 to the minus 7. Now, one will work on the third ionization process where hydrogen arsenate ion in liquid water ionizes partially to produce hydronium and arsenate ion. Ka3, or the third acid dissociation constant, is 3.2 times 10 to the minus 12. In constructing the Rice table, the initial concentration of hydrogen arsenate ion is 1.0 times 10 to the minus 7 molar. Arsenate ion has 0 molar, and hydronium ion is 5.2 times 10 minus 2 molar. The change is minus Z for hydrogen arsenate ion and plus Z for both arsenate and hydronium ion. The equilibrium concentration for hydrogen arsenate ion is 1.0 times 10 minus 7 minus Z plus Z for arsenate ion and 5.2 times 10 minus 2 plus Z for hydronium ion. The equilibrium expression for K3 equals the concentration of arsenate ion times hydronium ion divided by the concentration of hydrogen arsenate ion. If one plugs in the numbers, 3.2 times 10 to the minus 12 equals Z times 5.2 times 10 to the minus 2 in parentheses, divided by 1.0 times 10 to the minus 7 minus Z in parentheses. To determine if Z is small enough to ignore, one needs to take the concentration of hydrogen arsenate and divide by K3's value to see if the ratio is greater than or equal to 400. In the end, the ratio equals 3.1 times 10 to the 4, which is greater than or equal to 400. So as a result, the assumption that Z is small enough to ignore is valid. In the end, after rearranging the equation, the final answer for Z is 6.2 times 10 to the minus 18. The final answers are as follows. Since X equals 5.2 times 10 to the minus 2, arsenic acid's concentration is 0.45 molar. Dihydrogen arsenate ion's concentration equals X, or 5.2 times 10 to the minus 2 molar. Hydrogen arsenate ion's concentration equals Y, or 1.0 times 10 to the minus 7 molar. Arsenic ions concentration equals Z, or 6.1 times 10 minus 18 molar. And hydronium ions concentration equals 5.2 times 10 to the minus 2. The pH of this solution equals the negative log of hydronium ions concentration, or the negative log of 5.2 times 10 minus 2 equals 1.28. The percent ionization of arsenic acid equals the sum of X, Y, and Z portions ionized from the acid divided by the concentration of arsenic acid, which is after plugging in its values, is 10%.